My name is Anthony Liguori, and I am a Vice President and Distinguished Engineer in EC2. And I've led the design and implementation of the software part of the AWS Nitro System for about the last 10 years. And with me I have Ali.
My name is Ali Saidi. I'm a Senior Principal Engineer in Annapurna Labs, and I joined about 6 years ago to work on Graviton.
Great.
So Anthony, about a decade ago, AWS was thinking about what Nitro would be, and about 8 years ago, you bought Annapurna Labs. What problems was Nitro trying to solve?
We were really trying to solve a whole bunch of problems all at once, as is often the case in these types of big initiatives. So one of the big things that was happening about a decade ago was there's this fundamental change in how I/O worked in the cloud. So before about 10 years ago, the prominent standards were 1 gigabit networking and hard drives, spinning magnetic hard drives. And those technologies really hadn't changed much over 10 years. The performance didn't improve much. And for the most part, with virtualized-based systems, we all just did the emulation and software, and that was good enough. There was really no real problem handling that type of I/O load.
Then
we got 10 gigabit networking, and you get an order of magnitude more performance. And with software-based virtualization, you have to devote CPU to do that emulation. So while we were able to offer platforms that supported 10 gigabit networking, there were really two problems with that. One is that not all workloads could really get the same performance, especially with small packet sizes. And two, in order to offer that performance to multiple customers and not devote the entire server to handling I/O virtualization, you ended up having to oversubscribe and have variable performance. And what we were really hearing from customers is that they loved the performance, they didn't like the variability. And the only real way to solve this problem is hardware. We had to move all that logic into some form of hardware. And so that got us looking at, okay, we know we have to do something with hardware. What should we do? Should we just do I/O virtualization, or should we do more? And that's really what started us on the journey, is that question of, okay, we're going to do hardware. What can we do, and what are the problems that we can solve? Now, we say that we went and we built hardware, and a big part of that was finding Annapurna Labs. And Annapurna Labs was a really special company because ultimately they were building software, or they were building hardware that was easy to use from a software perspective. And it's one of the reasons we were able to move so fast. But when we say they were building hardware, I don't think most people know what that means. What does it actually mean to build a chip and to build custom hardware like this?
Yeah, and the reason is people can mean a lot of things when they say that. 10 years ago, I purchased a new home, and I was telling people, well, I built a house,
Sure.
right? But I wasn't swinging a hammer, I wasn't doing the plumbing, I wasn't even deciding where the plumbing and electrical and things went.
Sure.
I just kind of had some high-level idea, and other people did all the work, right? But in Annapurna, we mean something really different when we say we built a chip. We mean we own the end-to-end design, from the high-level architecture, through the design process, the implementation, ultimately the testing and delivery of that chip. We've been building these Nitro chips now, and Graviton chips through multiple generations. We announced our 5th generation back at reInvent in November, and that's powering 2 instances. Actually, we GA'd yesterday, the C7GN and the HPC7G instances, and we really designed these chips hand in hand together. We're running the EC2 software as part of the design process. This is very different from when you go and buy a third-party chip where the vendor didn't have that software. Actually, the two don't really want to talk to each other and provide that level of detail. And so people are kind of guessing, and you're ending up not really creating the most optimal solution. And with this partnership, we get to create that.
That's right. Yeah, I've worked in other hardware companies before, and the way that it always worked was that the hardware team would go off and they would design a piece of hardware in a black box way, never talking to the software folks.
Yeah.
And as a software developer, sometime late in the cycle, you would get handed a specification, and then you'd have to go figure out how to use it. And that's radically different from the way we do it, right? We're working
Absolutely.
early.
I mean, I've seen places where the software engineer isn't involved until the silicon's back and brought up, and a board lands on their desk, and they're now make it work.
Exactly.
And it's okay. And yeah, it's very, at least unoptimal solutions, where if you have the iteration cycle that's that long, that it's generational iteration to fix things, not continuous iteration. And we get to do the continuous side.
Right, and so a lot of the folks that I imagine watching come from a software background, and they're used to the way that modern software is developed, which is very iterative, as you mentioned. And so that might mean that you're deploying software every week as part of a CI/CD pipeline, and you've got integrated testing, and you're really just doing it small bits at a time. But that's not really how we develop hardware, right? So can you talk a little bit more about what it looks like to develop hardware and how we do that in order to make iterate so much on the Nitro technologies?
I mean, the software development process, like the hardware one, there is source code. There's usually an HTML language like Verilog. It's a really popular option. And there are even tools that look a little bit like compilers. They take that and turn it into something that's eventually manufacturable, but there's a lot more iteration and it's not just to push a button and walk away. And one of the big differences is while we can build, test, and deploy software in hours or days or maybe weeks, depending on the time frame, to building a chip, every iteration costs many millions of dollars, and it takes really many months. And so if you just end up with one bug, just one, you can slip your launch by half a year at just great expense. And that really means that the testing and validation of that design is just hugely important. You need to do a lot of it to make sure it's going to work as expected. But one of the really difficulties is while like this chip here will run at a little over 2 gigahertz, an emulator or a simulation will run 1,000 or 10,000 or even 100,000 times slower than that. And that makes it difficult to cover all the scenarios you might want and to test things. I mean, if you think about it, you have a test or a benchmark that takes 1 hour to run. That can take months or even years with those kinds of slowdowns. So it's just not possible to do.
It's not very continuous in terms of iteration.
No,
Totally.
well, you just can't run it. Like, you can't afford that in your design cycle. And so, in Annapurna, we do traditional stimulus-based testing, kind of like unit tests. But from the start, we also done a lot with formal verification. With the traditional unit test, you have some stimulus, some input, and you check the output was what you expected. But you can only do that kind of for the tests that you write, and maybe you can get a boundary condition here or there. Formal verification is really much more powerful. It lets you mathematically prove that for this input, you get the correct output for all inputs and outputs. So we do a lot of that. And actually joining EC2 also allowed us to adopt the cloud as part of our design processes. And we get to burst into EC2 capacity as we need it during the design cycle. And so we can scale up the resources and scale them down and not have to pay for having those servers in a closet for a long time. It's also a lot of fun because as we've done this, we are now doing more of our electronic design automation on Graviton. We're moving more workloads there.
Oh, really?
Yeah.
Oh, wow.
And so we're taking the current generation of Graviton, the current generation of Nitro, and we're using them to develop the next generation. And it's really fun.
And I imagine one of the other big things, I'm a big believer that the only way to really do something fundamentally better is to simplify the problem. And you talked a lot about the importance of validation. Because we are building the hardware specifically for the Nitro system, we're not building general purpose products, we're trying to sell to a bunch of different use cases. It really lets us focus in on the key things that we need and our customers need, and make sure those things are absolutely perfect.
We can totally focus on getting those right.
That's right.
And not just trying to add every kind of feature that someone might want, because we haven't found a customer for it yet, for example. And that adds much more complexity and much more verification and much more testing requirements and just makes it take longer. And so,
absolutely.
It's a big thing. So we've gone from generation to generation. I mentioned we're on the 5th generation of Nitro card now. Can you talk about what changes have happened in that time and kind of what we've done since you first started?
Yeah, the most obvious change is the cards have gotten bigger, right? So we actually have 2 cards here with us. This is the Generation 4 card and the Generation 5 card. So the very, very latest and then the previous generation before that. And you can physically see the cards are getting bigger, and that's because we're adding more capabilities and functionality. And so in the earliest days of Nitro, the big thing that we focused on was taking our existing EC2 features and just offloading them. So we offloaded VPC, we offloaded EBS, the normal things. But the cool thing is that in the last few years, we've been starting to really innovate and introduce new capabilities that would not be possible in any other form other than building our own custom hardware. A great example of this is Amazon SSD. And so everybody's probably seen an SSD before. They're usually like little 2.5-inch boxes or so. What people don't realize is that there's usually a full-blown operating system in these devices that do all sorts of wear leveling and other types of algorithms, even garbage collection for the SSD. In reality, those devices are probably running Linux. Like oftentimes they're running that kind of level of operating system. They're usually not patched properly. They're usually not monitored well. And by using the Nitro Silicon as part of Amazon SSD, we actually can have really strong ownership over the platform. We can drive down costs, and we can introduce a lot of cool features within the SSD level. Obviously, one of the big things that this has enabled us to do is introduce the Nitro Hypervisor. And so when we show you these cards, the thing that's really important to understand is that all of the software that we need to run the EC2 and AWS overall really is running on these cards, not on the CPU that your workload is running on. That means that entire CPU, whether it's a Graviton CPU or even an Intel or AMD CPU, is fully available for you as the customer to consume and to get all of the benefits from.
Yeah, it was pretty amazing when we first brought up the first thing that looked like the A1 instance. Yes. We stuck a Nitro card in there. It's the same Nitro card that was in a C5 instance.
Right.
And doing no work effectively,
yes,
it started to look like an EC2 instance at that point in time.
Which is really amazing because having worked in this space my entire career, you're used to porting to an ARM architecture, that's going to take years and years of development effort, years and years of work. Reality for us, it's actually been really easy, and we've been able to just iterate and introduce these really cool technologies.
Yeah, and lots of instance sizes, shapes, and kind of a huge breadth.
Yeah. So you mentioned earlier that when we build these cards, the cost of getting it wrong is pretty high. You have to potentially respin, take huge delays. You mentioned simulation can be really slow too. So how do we actually know that we're going to get the right hardware? And most critically, when we're building a card, we're building it to hit a certain performance amount. Whether it's, our latest generation cards can do 200 gigabits of networking. How do you know before you actually have silicon in hand that we can achieve 200 gigabits of networking in a card like the 5th generation Nitro card?
Yeah, one of the best parts about working at AWS is that unlike other silicon manufacturers, we get lots of direct customer feedback. Both from external customers saying, it'd be great if you could do this, but also from Anthony and his team saying, no, we can do better here. And so we know when we've hit the mark, we know when we can do a little more there. And as every generation, we get to feed that back in, and there's kind of a flywheel that's spinning faster and faster and faster there. In a lot of, as we talked about earlier, a lot of companies, hardware design's done, then the software engineers get to touch it for the very first time. Right? And they're going to find things that are wrong. They're going to have workarounds. They're going to find things didn't perform right. And really the biggest difference about how we operate is that the software engineers are part of the design process from day one. Right? The hardware engineer is designing the hardware, and right next to them is a software engineer. And early on, they're building hardware abstraction layers and making sure that we can have a same way to program the hardware, get that functionality, and that same software is carried throughout the process. We use that in testing, but that's also the software that pretty much ends up being run in production with a bit more polish. Yeah. So there's that feedback loop isn't generational of, we could have done that better. It's really continuous.
Yeah. There's an example of this in the Nitro Silicon that I really love actually, because it shows you what usually happens in the industry. So normally if you're a software developer and you get given a new piece of hardware, particularly a system on a chip like we have with the Nitro cards, you have to write a bunch of software to deal with the network device, and then it's a bunch of new software to deal with other accelerators. And one of the things that's been really great working with Annapurna is they recognize early on that software is really all about reuse. And having the same hardware interfaces on a bunch of different parts of the hardware means that as a software developer, you can write code once, you can test it, you can get it really focused on it being correct, and then you can use it for a variety of different hardware devices. And it's really that kind of understanding what software developers need and then building the hardware around that.
We keep consistent generation over generation.
And this has been really huge in letting us iterate fast.
We also do that with ENA, right? We developed the ENA driver, and we've seen it go from 10 gigabits up to 200 gigabits now. Same driver, you don't have to change it in your instance. It's not, there's some new features, please update all your AMIs.
And this would never happen on premises. On premises, those are multiple generations of physical different NICs with different drivers. You'd have to rebuild all of your images, figure out how you're going to deploy all the software, requalify, and on top of Nitro, it just all magically works.
Yeah.
Right?
And we've also been developing technology that lets us emulate Graviton and Nitro cards together. When people talk about processors, they almost always talk about kind of industry standard benchmarks, and those are suites that have been studied and minimized to run on systems. But in a lot of times, that isn't what the system's going to do or anything really close to it. And so we've been taking an approach of being able to put a system in the lab and pull a workload off of that, put it in the emulation, see what the performance is going to be like.
Wow.
Taking a graviton and a Nitro card, putting them together in emulation, seeing packets flow. No real hardware involved yet.
Yeah.
But like that early in the design process, so we can get confidence that this is all going to work. We're going to get the performance we expect.
Right.
We're going to see the benefits that we expect.
This is another thing I think a lot of people don't realize about the way most hardware and software systems work is that the hardware is always way more capable than what software is able to drive out of it, because it's actually very hard to understand why you're not lighting up every single part of the silicon. And sometimes getting into a simulator is the only real way you can figure out that, oh, I've got a bubble in my instruction pipeline because I have a data dependency on this and something like that. So being able to run these real world workloads that include the EC2 software stack in a simulation environment, including Graviton and the Nitro cards, means we can actually get lots of performance out of the system that you're probably not getting on most hardware platforms.
Yeah, and we can really see where, like you said, there's places where there's bubbles and we can do better.
Absolutely.
So, we've been adding hardware features like we've been talking about. What are some of the recent ones that you found most exciting?
Well, again, the thing that excites me the most are the innovations that are only possible because of things like the Nitro system and the hardware that we've built. A great example of this is SRD. So this is a reliability protocol that we've built. Most people don't realize that TCP/IP is a really, really old protocol. I mean, we're talking 40 years old or so at this point in time. It kind of makes me feel old to even say that, honestly, but it is what it is. It's not really designed, it's designed for the internet. It's not really designed for data centers and super low latencies. And so to achieve really low latency for things like EBS storage, or even for customer workloads or for HPC workloads, you really need something other than TCP. And asking customers to build their own protocols on top of UDP is really difficult. I mean, congestion control is that type of problem that there's only a handful of people in the world that should ever be touching it. It's just that hard. And so with SRD, we were able to build a protocol that was really optimized for our data centers and optimize it with silicon so that customers can get the benefit of it from a performance point of view. That's also led to technologies like EFA, which allows customers to do RDMA on top of EC2 instances without having to have dedicated fabrics like InfiniBand. This means that they can have the full elasticity of the cloud. They can launch lots of instances, and there's no limit on cluster sizes.
Exactly.
Again, and only this would be possible by building silicon that can optimize these things, because we're talking about single microseconds of latency, right? The other really exciting thing, this goes back to some of the security improvements, is encryption. So we mentioned how difficult it is to handle 10 gigs of networking in software, and it's even more difficult to handle 100 gigs. But with the Nitro system, we're actually able to do 200 gigs of networking in the Generation 5 cards while doing encryption completely transparently. Yeah. You cannot do that in software. There's just, a modern processor cannot do that purely in software. You have to do dedicated hardware. So it's things like that that really, really excite me, because we're really delivering things that customers could not do with general purpose hardware. There's just no way it's not technically possible. We've talked a lot about how we design the Nitro silicon and all of the ways we get to good quality. But another really important part that we all spend a lot of time talking about and thinking about these days is efficiency and sustainability. So can you talk a little bit about how building our own hardware helps us achieve some of our sustainability goals?
Sure. I mean, generation over generation, we've adopted newer process nodes and built more functionality into each card. And one of the reasons we can do that is really our scale. Building silicon is super expensive, but we can amortize that across all of our servers, and even small benefits in reducing energy or components ends up being a big sustainability win. Before I came to AWS, I didn't know what the word dematerialization meant, but it means to remove the materials in a solution or reduce them. And in Nitro, we've evolved over the years. If we had some of the older cards, from 2 chips to 1 chip, from 2 cards to 1 card, we've gone from 10 gigabits to 200 gigabits. We've gone from systems with kind of a handful of CPUs now to 48x large systems with a single card. And every time we do that, we just get to do more with one piece of hardware. And if we're only making one piece of hardware, it's just more sustainable. Yeah. It's less materials. It's great. One of the places that we've done this most recently was Graviton 3. Most servers have 2 sockets in a 1U server. And with Graviton, we did something kind of odd. We put 3 in there. And it took work to do that. Like, we had to make sure the 4th generation Nitro card could support talking to 3 sockets instead of 2. We had to make sure that the package of the Graviton CPU, the heatsink, the motherboards would all fit like side by side. But doing so for the same amount of compute reduced lots of stuff. Less sheet metal for racks, less sheet metal for servers, fewer Nitro cards, fewer power supplies, and a bunch of other components. And being able to do more with each server is just a huge sustainability win as well.
Yeah, absolutely. It's amazing how I think virtualization in cloud really just enables so much more efficient usage of hardware compared to if literally every workload was running on top of a bare metal server. I mean, that would almost be catastrophic. Yeah. One of the things I absolutely love about working in AWS and specifically working on Nitro with the broader team is that we obsess about individual watts of power consumption on a server, because multiplied across the scale of AWS, the savings are really big and meaningful.
It's just huge. So we covered a lot of ground, but we haven't talked about security yet. And Nitro's enabled really a different model there.
That's right.
And I don't know how much people appreciate that, but I think we should spend a few minutes talking about it.
Absolutely. So security is the most important thing we do at AWS and certainly in EC2. And I mentioned there were a lot of things that drove to the creation of the Nitro system, and one of them was that we wanted to make sure that EC2 could support even the most sensitive workloads out there and have the highest possible security bar. Really, and I fundamentally believe that with the AWS Nitro system, you are more secure than you could ever be even in your own on-premises data center. A lot of what has gone into doing that is that we built every single bit of software from the bottom up to support 2 big things. One is to have no operator access. So in fact, we feel so strongly about this that we even had a third party recently evaluate our system and release a study about it, the NCC Group, UK-based cybersecurity firm, confirming that we have no operator access to customer data or even service access to customer data. And we've changed our terms of services in EC2 to even further that commitment that we don't have access to that data. We operate our entire EC2 fleet without any human being able to log into a server or
just nothing to log into,
upload custom code, because there's nothing on those cards that what you would allow customers to log into, or sorry, us to log into. The other big kind of game-changing architecture change in the Nitro system is that all of our software runs on these cards, but the customer's workload runs on the general purpose CPU. And we actually have a physical separation between our software and the customer software. That means 2 things. One is there's entire classes of vulnerabilities and security concerns that just don't apply anymore. Like, there's a lot of talk about side channel vulnerabilities, and we have a lot of protection because of that separation. The second thing is that our hypervisor we were able to dramatically simplify. There's no networking stack. There's no file system drivers. There's no storage drivers. There's so little in our hypervisor. And fundamentally, even though everybody believes they write great software, I think everybody thinks that, there's just a relationship between the number of lines of code and security bugs. It's unavoidable. It's just the way the industry works. And so having a smaller surface area fundamentally means that you're going to have a better security posture. So yeah, and the final thing to mention in this space is that we haven't talked at all about the Nitro security chip, but we've also been innovating on the motherboard of the server itself, and we've built something called the Nitro security chip that allows us to protect the system and all the non-volatile storage in the system from any kind of firmware-based attack or concerns of that nature. So really, we've been able to do a ton of things based on the Nitro architecture, and I'm sure there's tons more that we're going to do in the future, as it's really enabled us to have a type of innovation that we could not achieve any other way.
Yeah.
So. Great. I really appreciate everybody taking the time to listen to us today, and hope you enjoy the rest of AWS Silicon Innovation Day.